We're online now. Uh, Want to finish what we were doing last time about mass and center of mass. Just to comment, the final exam's coming up soon, so around Monday I'm going to put a list of final exam practice problems. You can look for it then, and we'll Friday of next week, maybe some on Wednesday, we'll do review problems for the final. Okay, so think about what you want to look at. You can finish up the homework all but one section after today, and look for the review problems on Monday or thereabouts. So last time we had a plane region, we wanted to apply integration methods to find the mass and center of mass of this plane region, or let's call it, and we did this kind of a formulation. We made a continuous analogy to the discrete model, right? And where in the discrete model, you just took the average position of mass. In this continuous model, we had the moment about the y-axis. That's the balancing point actually in the x direction, somewhere here. Let me finish this first. The moment was defined to be the integral from a to b of x times f of x, f1 of x minus f2 of x dx, right? And that gave you an analogy to the discrete model where you took the average, you took the moment of mass in the x direction, and then you took m, the mass was the integral from a to b, and I forgot rho in here. Rho, they like to put it outside assuming it's constant. Rho f1 of x minus f2 of x dx was the mass, and then you can compute the x coordinate of the center of mass by taking the moment divided by the mass, and that was the average position of mass. So hopefully that looks familiar. And then here's x bar right here where the fulcrum will balance this thing. With that in mind, we want to make a similar computation to find the moment in the y direction, right? We mentioned that you could do that, but how do you find the moment in the y direction if it's bounded by a top curve and a bottom curve? You can say, well, similarly, if you have a region that goes the other way, between y equals c and y equals d, a left curve, x equals g2 of y, and a right curve, x equals g1 of y, and you have a plane region, you can say, oh yeah, well, mx, the moment about the x-axis in the y direction, ought to be the density times integral of y times g1 of y minus g2 of y. Exactly the same thing, just with different letters because you're integrating the y direction, dy from c to d. And then the mass can also be calculated as the density times the integral from c to d. The same integral, just leave y out, right? g1 of y minus g2 of y dy. And so that actually leads you to formulas for calculating the mass. If it's this kind of a region, you just integrate g1 minus g2 times rho. And if it's in this direction, just integrate f1 minus f2 times rho. And then, of course, the balancing point y bar in the y direction could be written as mx over m, right? So we can do this kind of a calculation. Then, if you turn the plate on its side, we said you could balance it at the point x bar, y bar, and it wouldn't tilt in either direction, right? So I wanted to do at least one example with that. And then also, if there's a line of symmetry, we'll make this following note. You don't even have to do that calculation if the region R is symmetric across a line then it balances at that point. So you can compute X bar by inspection. And then an obvious notice here, but if I just left the rho off of here, what would this be instead of mass? On this one, or this one. I'm integrating F1 minus F2, so I get, yeah, the area between the two curves. So all this is doing is saying for constant density, the mass is just the density per unit area times the area. That's all it's saying there. However, I just wanted to point out the book doesn't mention this because they're going to do a better job with it later in Calculus 4, but 3. But if rho actually depends on x only, you can put it in here and find the balancing point where maybe the density varies with x. And similarly here, if rho varies only with y, you can put rho in times inside the integral and calculate these things still. The problem is when it depends on both x and y, then these formulas don't work, right? So you have to deal with those later. All right, so let's do one example here then. Suppose I have this. Find the moments mx and my and center of mass for the solid, the plane region that looks like this. It's between, we had this for part of last time. Y equals x squared and y equals 9x. That region. Guess I got to get rid of this. I was trying to save it, but I couldn't do it. All right. If rho equals 2 grams per square centimeter. All right. So we said that you could compute the moment my by doing the same integral as if you were doing area or mass. Let's do the mass first. The mass is the double integral of the top function, 9x, minus the bottom function, x squared, dx, right? You just take the area integral, top function minus the bottom function, integrate it. Oops, I wrote double integral. Getting in a habit here. Going from this point here, where it begins, to this point here, which was 9. So I integrate from 0 to 9, we said. And we come up with twice for rho, integral 9x integrated became 9x squared over 2. X squared became x cubed over 3. Plug in 0 and 9 and take the difference. And we get 9 cubed over 2 minus 9 cubed over 3 is 9 cubed over 6. Right? And so this became 243, I think. Let's see. Yeah, 243 grams then, right? Grams per square centimeter times square centimeters from the area gives 243 grams. All right, so there's m. And then to compute the moment, all you have to do is put the same integral. You put rho times the same integral. but put x in there. Right? So you don't have to rework anything but put the x in. And that gives you my to put x in. Now I have twice the integral from 0 to 9 of 9x squared minus x cubed dx. Gives me twice 9x cubed over 3 gives me 3x cubed. And then minus x to the 4th over 4. Plug in 0 and 9 and take the difference. Right? So I got to get rid of part of this. All right. Maybe I better run this one on my calculator again. All right, looks like I get 2187 over 2. And then I can compute the center of mass coordinate in the x direction by just taking the quotient of those. Right? 2189 over 2, all divided by 243. Comes up with 9/8. That doesn't seem right. Let's see. I just double check this real quick. Oh, ha. I know what. Let's see. I know what I. No, that's right. That's right. Well, it comes out right. It just doesn't look right. That's all. Maybe my division was bad. Let's try it again. That's strange. Yeah. All right. This one was, I guess I just pushed the wrong button on the calculator. It's 2187 over 486. The integrals are right. There we go. All right, and then that's the balancing position on the x-axis. So then you do the same thing on the y-axis to do it the other direction. I then have to write x as a function of y. So I'll do the same thing in the y direction. I'll compute mx and m. Well, I can use the same m I had before, but I have to rewrite this now. This is x equals square root y, and x equals 1/9 x, right? 1/9 y. So mx is then the integral y going from here to here, which is also 0 to 9. I'm sorry, no, 0 to 81. If you're at 9 here, then this is 9 squared is 81. And you want to take y times the right function, square root y. And here's, be careful on this when you want to find the right and left function. Just draw a horizontal line. The one that intersects more to the right is the right function. So square root y is the right. Minus the left is 1/9 y dy. And you can compute this integral. This time, with a little integration, you get 19,683 over 5. Then you divide by the same mass to get y bar, coming up with 81 fifths. All right, so now you've got the center of mass is 2187 over 486 and 81 over 5. So there's how you can calculate that to go both directions. Unfortunately, what happens once in a while is you get a region that's not easy to describe in both directions. Like in one direction, you can write a right function and a left function, but the other direction, you can't write a top and bottom so easily without breaking it up into a bunch of pieces. Or you can do the top and bottom, but not the left and right. So we want a formula that works for those too. So we'll make the following note. If R is given, again, by all x, y, such that A is less than or equal to X is less than or equal to B, the first kind of region we had, and Y is bounded between F2 of X on the bottom and F1 of X on the top, as before. Does not have an easy left-right analogy such in the last picture, we can do the following setup. And this illustrates one of the powers of calculus to be rather abstract. There was, in the ancient Greeks, they had this terrible problem of doing things like, what is the formula for the area of the circle? And you could use that to try and estimate pi. And so they would insert a bunch of these polygons in here, and then to take more and more sides, and you could estimate pi by taking polygons with more and more sides and say, well, it's bigger than all these and it's smaller than all these. And that was a terribly slow thing, but Newton's calculus made a lot of this a whole lot easier because you could abstract. And here's how you abstract this thing. You say, suppose we consider the region like this, and it's just got the one orientation, y equals f2 of x, y equals f1 of x, between a and b. Let's do it like this. All right, this would be terrible. You have to go between these two curves till you get down to here, and then you have to go between this one and this one till you get down to here, then between this one and this one and this one. And trying to break it up into a left and right function isn't so easy. What you can do instead is the following. Suppose we do slabs like we did for the water pressure problem, right? And we'll break this up into little increments like this in x. Oops. And so we'll call this a x naught, x0, and then we've got x1, x2, and so forth on out to b is xn. And how can we find the balancing point in the y direction using that kind of thing? Well, you can look at the kth little slab here. So the kth rectangle, we'll call it. And if this is uniform density, which is what we're assuming in here, or if density is just a function of x, then we know what the balancing point is for a rectangle like that, right? It's right halfway in the middle. So if this is taken at some point, xk star for the k slab is where you have this function going through here and the other function going through here. So you take the height between those. That's what, right? The height between these two functions, f1 of x and f2 of x. The balancing point is halfway between there. So we know for this particular thing, this is at 1/2 f1 of xk star. Need more room. 1/2 f1 of xk star minus x, or plus f2 of xk star. It's the point halfway in between. You just average the two. Right? So that's where that one's going to balance. And you can treat this as though in a uniform gravitational field, as though it was a point mass all at this one point, right? Halfway down. And so now you can think of adding a whole bunch of these together as though it was a whole bunch of discrete masses. And you say that the balancing points of all these little rectangles now comes like this. Y bar is the sum of the moments. So we add up the moments on the top. Actually, let's do mx first. The moment is then the sum of these points. We need y we need yk bar, the balancing point for the kth thing, and that's what this is. Yk bar is the balancing point for the kth slab. Times the mass of that one. But the mass of that one is the density times the area of the rectangle, which is base times height. F1 of xk star minus F2 of xk star. Where you take xk stars at some point in the kth interval. And so this is the kth area times the density gives the kth mass times the balancing point as though it was sitting all at one point here. All right, so that's an estimated moment. Then if I take the limit as the number of slabs goes to infinity of the sum over those n slabs, then I'll get the balancing point, the moment in the y direction by this formula. Well, what is this? You see what that is? If I take a limit of a sum, let's rewrite it a little bit. This is limit n goes to infinity. And I can pull the row out. Sum k equals 1 to n. Yk bar now gets replaced with this formula. 1/2 f of xk star plus f2 of xk star. And then delta x I'll put on the end, and I'll put row out front. So I'll just multiply by this next. F1 of xk star minus F2 of xk star. And then here's the delta x. So I'll rearrange it and I'll replace yk bar, the balancing point for the k slab, with this formula. It just says it balances in the middle by symmetry. And now I have that formula. Now do you recognize what it is? Yeah, it's an integral. In particular, this thing, since it's a sum and a difference multiplied together, right, by our algebra formula, this is f1 of xk star squared minus f2 of xk star squared. That's what this multiplies out to be. All times a half, I can pull the 1/2 out, and we'll say this is 1/2 row limit n goes to infinity. Sum k equals 1 to n. This times delta x. I should have said delta xk here. Delta xk, the width of the kth interval, delta xk. And there it is. This by definition is the definite integral from a to b, since we're incrementing x, of this function. Just put in x instead of xk star, so it's f1 of x squared minus f2 of x squared. And delta x becomes dx. The definition of the definite integral says that you get this formula. So there's the formula you can get if you have trouble writing the regions between a left and a right curve. And then you can use the same formula for the other. You can use the other formula for the x, the moment in the x direction. So let me try this one just for fun then. Suppose I wanted the center of mass if the region looks like this. This is at 4, and this is the curve here. Y equals I need to move this a little bit. X squared plus 2, right? And it goes, say, from x equals minus 1 to x equals plus 1. You have that kind of a region R. So maybe you'd rather not break this up into being between a left curve and a right curve because it has, right, you've got 2 pieces in here and then you've got 1 piece in here and that kind of thing. So how can I find the moment of mass in the y direction here? Well, I can use this last formula, and we'll say the moment mx and along the y-axis for this is now, if we treat it as a vertical region, this is the f1 of x, the constant, the top function. The bottom function is just y equals 0, so this is f2 of x. And now we can do an integration with respect to x, which is easier. And we'll say this is 1/2 rho. We'll leave rho undetermined here. Going from minus 1 to 1, right? The top function squared, which is x squared plus 2 squared, minus the bottom function squared, 0 squared, dx, right? So I can do this integral, it's easier. And this one can be done with a nice substitution, right? This is 1/2 rho. And if I substitute, well, actually it's not. Integral from minus 1 to 1. Rewrite this as x to the 4th plus 4x squared plus 2 dx. Then we come out with 1/2 rho integral from times x to the 5th over 5 minus 4x cubed over 3 plus 2x. Plug in minus 1 and 1 and take the difference. Right? And then you notice by symmetry, plugging in 1 and minus 1 is equivalent to twice if you just went from 0 to 1. Right? So this is 1/2 rho, 1/2 times 2 becomes just rho, x to the 5th over 5 minus 4x cubed over 3 plus 2x, plug in 0 and 1. So it's twice the integral from 0 to 1. So I'll say this is 1/5 minus 4/3 plus 2. All right. Yeah. So I think it comes out to be 7/15. Yeah. 7/15 rho, whatever the density is for that one. All right. Now, when you go to compute the moment or the center of mass, you can then just compute the mass with the same integral, going from minus 1 to 1 of just the top function minus the bottom, which is x squared plus 2 minus 0. So that's f1 minus f2 dx was times rho was the formula for the mass, right? So I wind up with rho times x cubed over 3 plus 2x, a little easier integral from -1 to 1. Once again, by symmetry, this is twice rho times x cubed over 3 plus 2x evaluated at 0 and 1, which is 1/3 plus 2 gives 7/3 times 2 is 14/3 rho. For the mass, all right, well, there's a mess up in all those fractions in the last problem. The value of mx, if I take x plus 2 squared was x to the fourth plus 4x squared plus 4. When you integrate that, all times rho, gives you 83 rho over 15. You can then compute the mass using the x formula, integrate from -1 to 1, the top function minus the bottom function, times rho. You come up with 14 rho over 3. And then y bar, the balancing point along the y-axis, is just mx over m, is this one divided by this one. Comes out to be about 1.2. So the region that looks like this, if this is 2 here, y equals x squared plus 2 on the top, y equals 0 on the bottom, balances it about right here, y equals 1.2 on the x-axis. Thank you.